Breadth first search in graph. Breadth first search is a fundamental graph traversal algorithm that explores vertices in the order of their distance from source vertex. So in a graph, you generally don't have any root node like a tree. In a tree, you always had a root node. So whenever you want to do any search in the tree or you want to traverse through the tree, you always know that this has to start from the root itself. So the starting point for all your tree algorithms is already very clear for you. You have to start from the root itself. But this is not the case with a graph. In case of graph, it doesn't have one particular node that is designated as the root. Instead, what you have is you are allowed to start from any vertex. So whichever be the vertex you want to start from, you will call that as the source. So let me call this vertex as the source. If this is my graph, these are the vertices in my graph. I'll draw edges as well so that this will be a complete graph. So this is my graph, okay? What I want to do breadth first search in this graph. First thing, even though it is called as breadth first search, we are not searching for any particular element. So this is something you have to keep in mind. In tree, whenever we said search, we were actually searching for one particular node or one particular value in a tree. In graph, generally, whenever we say breadth first search, we won't be searching for one particular element. Instead, we'll write an algorithm in order to visit all the nodes of this graph. The reason is, even though this is actually traversal, it is generally called as breadth first search only because this algorithm originated as a trick to search something from a graph, and later it was generally used whenever you want to traverse through the graph. So what we are going to write is a traversal algorithm actually, but it is called as breadth first search. Okay. So our aim is to start from the source vertex and visit all the vertices in the graph, and also you will, let us say, print in between. Whichever vertex you are visiting, you can print. Okay. First thing, why is this called breadth first search? Because you always prioritize breadth over depth. What is this? This means you will always visit all adjacent vertices of a vertex before moving on to the remaining vertices. That is, if you are starting from this source vertex, what will you do? You will first look into the adjacent vertices. What are the adjacent vertices of S? Let me name all of the vertices: A, B, C, D, E, F, G, and H. Here A and E are the adjacent vertices of S. Why should you always go to the adjacent vertices? Because the rule is, because it is breadth first, whenever you have a vertex at a lesser breadth, that should always be visited first. And how are you counting the breadth? You are counting breadth by checking the distance from the source node or the starting vertex. So all the nodes or all the vertices that are at smaller distances from your source will be visited before visiting any vertex that is at a larger distance from your source. So in this case, A and E are both at a distance of 1 from your source vertex. So you will always visit A and E before visiting any other vertex. And after that, what is the second step? How many vertices are here which are at distance of 2 from the source vertex? You can see that B is 2 steps distant. D is also 2 steps distant. Like if you want to reach D, you can go from source to A and A to D, or maybe source to E and E to D. So it is at a distance of 2. Similarly, F is also at a distance of 2. So after A and D, you should complete visiting of B, D and F before you can move on to any other vertex. So this is the logic you want to follow. Whichever are at a smaller breadth should always be visited before going to any vertex at a larger depth. So this is the logic you want to use in breadth first search. Let us see the algorithm. How do you write the algorithm for using breadth first search? So in this algorithm, you will be making use of a queue data structure so as to keep track of whichever are the nodes or vertices to be visited next. What you will do is, you will initially start from the starting vertex. So you have a queue initially. Into this queue, you will initially enqueue your starting vertex. So this is the only vertex present in the queue when you are starting the algorithm. In this algorithm, what you do is, you will first take out whatever is present as the first element in the queue. And once you took that element out, element in the sense a vertex. So once you took that vertex out, you will see which all are the vertices adjacent to this. Whichever be the adjacent vertices, that is, as soon as you took out, you are considering that you visited this vertex. That is, if your purpose is to print, you can print. If your purpose is to return the value, you can return the value, whatever. So you completed visiting as soon as you took it out of the queue. Once you visited this vertex, what should you do? You should enqueue all the vertices which are adjacent to it. So you will see which all are the vertices adjacent to S, and you will enqueue all those vertices here. Let us say A and E are adjacent to S. So once you enqueued, the benefit of this queue is, in queue, whatever entered first will go out first, which means given that you enqueued A and E, which are at a distance of 1 from S, that means whatever vertices you may enqueue after this, irrespective of that, A and E will always be visited before all of them. So this is the reason you are using queue, right? So the procedure is this: you took it out from queue, then you enqueue all the adjacent vertices. Once you enqueued all the adjacent vertices, what you have to do? All your work with this particular vertex is done. So you are done with visiting this vertex. After this, you continue the same procedure. Take the next element out of the queue, see what the element is, visit it, then enqueue all the adjacent vertices. If you continue in this same process, you will be doing a breadth first search. Whichever are the elements at a smaller distance from source, they will all be visited before going to the next distant vertex. What we'll do, we'll take a very small example that will be easier. We'll take the same graph that we took. Let this be your graph. Let this be the graph A. I'll call this S itself. A, B, C, D, E, F, G. Let us say A, B, C, D, F, G is good enough, or I'll shorten the graph. That will be easier. Otherwise, it will be very large. What we'll do, we'll have only this much is the only part of graph. Okay, this is the source. I'll have A, B, C, D, E, F, G and H. I'm going to start from S. What I'll do, initially I will have a queue. I'll enqueue S into the queue. What is the next step? Once I enqueued S, this is the beginning of the process. I have only one element inside the queue. So I should continue this procedure till the point my queue gets empty. So I'll take one element out of the queue. S is presently out of the queue. What will I say? S is visited. So I'll tick mark here to show that S is visited. Actually, what you do is you will maintain a visited array as well, and you will mark in it that okay, S is visited. Okay. Next step is S is taken out now. You will see whichever are the adjacent vertices of S. You know A and E are adjacent. So you will enqueue A as well as E. Once you're done with S. What will you do next? One more thing is, the importance of this visited array is that sometimes after you already visited a vertex, you may again get the same vertex as the adjacent vertex. For example, you already added A and E to the queue. Just imagine what happens when you are visiting B? At the point you are taking, at some point you will be taking out B from this queue. When you take out B, A will come as adjacent vertex of B. Then should you again enqueue A? Because you are already visiting A here. So you actually should not enqueue A again. Because of that, whenever you are enqueuing, you should first have a look into this visited array. So in visited array, if your element is already there, then you should not add it into the queue because that will be redundant. Because of that, you should not add whenever it is in visited. So what is the process now? A and E are here. You know S is already in visited. In visited, you have S, okay? I am taking A out. Which are the adjacent ones of A? B is adjacent to A. D is adjacent to A. S is adjacent to A. So S is already visited, right? So I don't have to add S. What about B and D? B and D are not part of the visited. So I have to add B. I have to add D. So A I am presently considering, okay? So E I'll put here. B is here. D is here. So A is also considered because B and D are both added. S is already visited, so I don't have to add S. Next is E. So A is also visited at this point. Next is E. What about E? E is here. If I see all the I'll first take E out. I'll say E is visited. Then, so this visited array and actually visiting, I'm considering these as two different things because in visited array, I want to populate as soon as I am entering it into the queue. Because if I entered into the queue, I'm sure that at some point I'll surely visit. So I don't have to enqueue the same element into the queue again because I'm sure that at some point I'll surely visit it because I already enqueued. So I should not enqueue it again. That is why I am updating this visited array whenever I am enqueuing it into the queue. But actually I am visiting that node only when I am taking it out of the queue and looking into it. Okay. So, okay, next. So E is what we are visiting right now. What will I check next? What all are the adjacent vertices of E? So E has S, D and F as adjacent. S is already in the visited list. What about D? D is already here. So whenever you are adding here, you should actually add it in this visited as well. So what this helps us, whenever you are having it in visited, you know you should not add it back here. So visited is actually an array in which you will make it, let us say 1 whenever you are already visiting, already added it to the queue. So you know E, S, A, E, B, D. These things are already there in your visited array. So whenever you are adding anything into the queue, you will first check into this visited array, make sure that the element is not there. Because if it is in visited array, that means it is already unqueued. Why are you not directly checking it in this queue? The reason is queue doesn't have direct access. If you want to check in queue, you will have to go to the starting, go to each element. So that will take up a lot of time. But this is array, dictionary, whatever you want. So in that case, you can directly access it in order of one time. If you want to check whether E is present here, you can directly check whatever be the index. So in that index, you will directly see whether E is present or not present. So that is your visited array. So array, set, whatever. So next thing is you are visiting E. From E you found S, D and F as the neighbors. S is already visited. D is also already visited. S, A, E, B and D. These are already visited. So you know D is also already visited. F is remaining. So you will add F into the queue. What happened now? You're done with E. Next is B. When you take B out, I'll say B is also visited. What is remaining? I want to check all the adjacent ones. C and A are adjacent. A is already in the queue. C I'll add into the queue. So I'm done with B. Next is D. When I take D out, what happens? See the order in which I am visiting. A and E are already completed. That is depth 1 is already completed. Then only I am going to the next depth. That is why it is a breadth first search. I'll search everything at the same depth, which means I am considering breadth first. In this breadth, I am doing a breadth wise search. That is what it is. So in depth 1, I had A and E, that is done. Next, I already looked into B. Next, I am looking into D. What are the adjacent ones of D? A, E, G and C are adjacent to D. So A, E, G is not present here. So I should add G here. So G is coming because of this. So I am done with D. I'll mark D also as visited. Next is F. So similarly, if I keep doing this, I will visit all the nodes. This is the logic of breadth first search. When will it complete? Whenever my queue is empty, I would have visited all the vertices of my graph. So this is the logic. So basically I have to go through all the vertices, all the edges. That is what is happening. Okay. So we'll write the pseudocode for this. In the pseudocode, what should we have? We should be having a starting point, a source vertex from which we'll start this complete operation. Then you should have a queue, right? A queue is required. This is where you will have a count of all the vertices that are to be visited, right? Whatever vertices you want to visit, you will add it into this queue. Another thing is you should have a set visited. What is the importance of this set? From this visited set, you should be able to identify whichever are the nodes which you have already added to the queue. Because if you have added once, you should not add again. Next thing is you should have a distance array or distance dictionary. Why should you have this dictionary? This is let us say optional, because if you want to know at what distance is each vertex present, if you want to store this information, then you can have a dictionary, and in this dictionary, when you are visiting each vertex, you will store whatever is the distance of that vertex from the source vertex. Okay, that is why you have this distance dictionary. So let us start with writing the pseudocode. Automatically you will understand. Okay, breadth first search of what should you have as input? One is you want your graph. So your graph, let us call is G, and you should have the source vertex. So graph means it is either adjacency matrix representation or adjacency list representation. Then I will have a source vertex. So source vertex is one from which I will start my complete search. So graph will represent my graph and source vertex will tell me where I should start my search. Okay. So firstly, what is the requirement? I should have an empty queue. Okay. An empty queue called queue. This is what I should initially have. After this, what should I have? I should have a set, let us say, called visited. Okay. I'll have a set called visited. I'm marking it as V. So this is my visited set. Where will I use it? I will use it in order to check whether this particular vertex is already present in queue or not, right? Third thing is a distance dictionary. Okay, a dictionary called distance. I'll call it D. These three things you should initially initialize. Distance is optional. If you want to keep track of distances, you can have it. If you don't want to, then it's okay. Right? Next thing is we'll start the algorithm now. So what did we discuss in the when we saw it practically? What is the first thing? We want to enqueue the source vertex to begin with. So first step is you want to enqueue into the queue source vertex. Source vertex is enqueued into queue. Next thing is whenever you enqueue something, whenever something is in the queue, you should add it into the visited set, because then only you will avoid adding this again. So because you are enqueuing S to the queue, what should you also do? You should also add this particular node S to visited, that is V. Into visited set, you are adding S. What is the next step? If you want to keep track of distance, you should also have this distance. Distance of S equal to 0. Why is it 0? Because you are finding the distance from the source. So source vertex is at distance 0 only. What is the next thing? Let me do this. Okay, so now is the time to start the main loop. Inside the loop, you have to keep taking each element from the queue, then see all the adjacent elements, and you should enqueue the adjacent elements after adding it in the visited array. Okay, visited set. So you will do while what should be the condition? While queue, that is while queue is not empty. Till the point you have something in the queue, what should you do? You should first dequeue the element. So u is equal to dequeue from queue. This means you will take the element at the least position or front of the queue and take this in node u. So u is presently whatever was the present in the front of the queue. So as of now, source will be present because source is the only element that you initially put into queue. What is the next step? You want to visit source. So let us say print u. So here you can add whatever step you want. If you want to return value, okay, return value. If you want to print, then print, okay. After this, what should you do? You should add all the adjacent vertices of whichever vertex you took out from the queue. So how do you find all the adjacent vertices? For each vertex, let us say v, which are adjacent to u. So in order to say adjacent to you, here what I'll do is, you have a graph, because initially you give graph as input here, right? To the algorithm we provided graph as input. So from that you have to find out adjacent ones. So here I'll mark as, for each vertex v in g dot adjacent, that is all the adjacent list of this graph of u. This means you have a graph and you know which all are the adjacent vertices. You want to find all the vertices which are adjacent to u. The reason I'm writing like this is, graph representation is what this will be dependent on. You may have an adjacency matrix representation. You may also have an adjacency list representation. If it is adjacency matrix representation, how do you find this adjacent list? In the adjacency matrix, you have to go to the row corresponding to vertex u. Once you reach that particular row, you have to go through the complete row. In that row, whichever vertex is having value 1, all those are adjacent to you. This is how you find it in adjacency matrix representation. In case it is an adjacency list representation, in the list, that is the pointer array, you have to go to the pointer corresponding to u. Once you reach that pointer, you will have a linked list which is having all elements adjacent to you. So either of these ways, you want to find out all the adjacent elements. So that is what this step is about. So here I am saying, for each vertex v in g dot adjacent of u, which means for each of the vertex v, which is an adjacent vertex of u in this graph. For each of the adjacent vertices, what am I supposed to do? I should first check if it is visited. That is the first step. If v is not visited, so not in my visited set. If it is not the, because if it is already visited, you should not be adding it back to the queue. This is an important check. If it is not in visited, what should you do? You should first enqueue it. You will enqueue into the queue the vertex v. What is the next step? After enqueuing, you should add v to visited, because now that you have enqueued it, you should add it to this visited list v, because this will avoid any further insertions of the same element into the queue. So what should you do? Add v, which is the adjacent vertex, to capital V, which is your visited set. Okay, so you added the value into visited set. So here you checked whether it is in visited set or not. You found it is not. So you enqueued and added it into visited set, so that Next time, if you enter this loop, it won't come inside this if condition for the same vertex. Okay. And one more thing is, if you want to keep track of distances, then you can update distance here, distance of V. What will be distance of V? You know, V is an adjacent vertex of U. So if V is adjacent to U, that means whatever be the distance of U, from there you have one more step towards V. So if you do distance of U plus 1, you will get distance of V. So this is how you will calculate distance of V. So once this particular loop is done, what happens? For whichever element you picked out of the queue, that is U, all the adjacent elements or adjacent vertices are now put into the queue. Then you will again go to this while. In this while, you will keep doing the same process. What will you do? You will keep taking next element from the queue till the point your queue is empty. Whenever your queue is empty, you will come out of this while, because the condition is till the point queue is empty. When queue is empty, what does it mean? You have completed searching through your complete array. So you can conclude. So let us say you want to return your distances. So let this be the final option to be done. So whenever your while loop is done, okay, this should be in the line of while loop only. Okay. So let us say here you have return distance. Let us just see algorithm once more, whatever we have written. In order to do BFS, what is the algorithm we have written? First thing, you should have a source vertex. Then you should have a queue. This queue will store all the elements, and this queue will maintain the order. The whole breadth first search order is maintained by this queue. Next thing is you have a set, which is V, which will keep track of all the visited vertices. So whenever you want to add anything into queue, at that same moment you will add into visited set as well, and you won't wait till you actually visit. The reason is, you know that if it is in the queue, then you are anyway going to visit it. So you can confidently add it to this visited set, because then you can avoid adding this again. That is the whole point. Next thing is dictionary. This dictionary D you are having so that you can keep track of the distances. Okay. What is the next step? You want to enqueue the source. Whenever you enqueue anything, you have to add it into the visited set. You added source into visited set. You marked distance of source as 0 because the distances are counted from the source. So distance of source vertex itself is 0. Next thing, you have a while loop which will run till the point queue is empty. Presently you have only source in the queue. What are you going to do in it? You will initially take one element out that is stored in U, and you will print it, visit it, whatever. After that, what do you want to do? You want to enqueue all the adjacent vertices of U. So you checked for all the adjacent vertices. For each of the adjacent vertices, what did you do? You enqueued the adjacent vertex after verifying that it is not present in visited list. After enqueuing, you will add that value into visited list. You will update the distance dictionary as well. So this much if you do, keep doing this for complete loop. What happens? For all the elements in your queue, you will take it out. You will see for all the adjacent ones will be added, and you will visit it. So whenever this is completed, this queue is completely empty. That is, you dequeued everything. That means your graph is completely traversed. You went through all the nodes in the graph. This is the graph breadth first search algorithm. Next thing is, let us see what are the time and space complexities of this algorithm. So where is the time used here? Let us first do time complexity analysis. What is the major part which consumed time in this case? So one part you can say is where you want to enqueue and dequeue each vertex. You have a queue and you know that whichever be the vertices you are having, each vertex you will be enqueuing once to this, which means it will take order of V time for enqueue and dequeue operation. This is right because you have a queue and you are aware that at some point every single vertex will be enqueued to this, and each vertex will be enqueued only once. You are sure about this. Because of that, order of V time will be taken. This is one point. Second point is, you will surely go through all the edges. This is also you are sure. Why are you sure? Because you will go to each of the vertices and you will check all the vertices, all the adjacent vertices. How will you check adjacent vertices? You will check whether there is an edge or not. So checking for the edge, how much time does it take? All the adjacent edges are explored. For that you will take order of E time. So now the question is, how did I find all the adjacent edges in order of E time? This is an important question here. So this actually depends on whether I'm using adjacency list or adjacency matrix. So let us see both the cases. We have adjacency list or adjacency matrix. So if it is adjacency list, what happens? You have an array of pointers. From this pointers, you have corresponding to each node, you have a pointer which will point to linked list of all the adjacent vertices. Okay. So for all nodes, you will have a linked list of adjacent vertices. What happens then? If you are going through all of these, at worst case, what happens is you will visit all these nodes once. And this is a must. You have to go through all these nodes because at some point you will go through all the adjacent nodes of each node. Why is it? Because we already discussed that from the queue, each vertex will be enqueued once and dequeued once. This is clear. Whenever you dequeue it, what will you do? You will check for all the adjacent vertices, which means if you will visit all the vertices once in the queue, that means you will check all the adjacent vertices of that vertex once. So in adjacency list, if you check adjacent vertices of all vertices once, that means you are going through all of these. And what are these? Each of these nodes represent an edge, because let us say this is of vertex A and you have new one B and C. What is AB and AC? Those are edges, which means if you are visiting through all these nodes in the linked list, all the linked lists present, you will be going through all the edges that are present in your graph, which means it is order of E. So in case of adjacency list representation, your queue, insertion and NQ and DQ of the queue will take order of V time, and visiting all the adjacent vertices, that will take order of E time. So total will be order of V plus E. So among V and E, whichever is larger, that will be the time complexity in case of adjacency list representation. Next thing, let us see what if it is adjacency matrix representation. What part is going to change? The part that is going to change is Q will remain the same. So order of V that is taken for the Q, that will remain the same. But what will change now? The change is, instead of this adjacency list, you have an adjacency matrix now. This time, if you want to check all the adjacent elements of any particular vertex, what do you have to do? You have to go through the complete row, which means you have to take order of V time for finding all the adjacent nodes of any particular node. So if you want to find adjacent nodes of first node, it will take order of V time. You want to take that of second node, again order of V time, again order of V time, and so on. Which means you already know all the V vertices will be enqueued once. This is right, which means they will be dequeued once. Whenever it is dequeued, you will check for all the adjacent nodes. That means V times you have to check adjacent nodes. Checking adjacent nodes already takes order of V time, and V times you have to do that operation, which means total time is order of V square. So in case of adjacency matrix, you will use order of V square time, and in case of adjacency list, you will take order of V plus E time. So there is a time difference between these two representations. Next thing is, what is the space complexity of this algorithm? So this is about time complexity. What about space complexity? Space taken is 1 is for Q, maximum what can happen in the queue, all the vertices can be present in the queue in worst case. That is, all the vertices can be presented once in worst case. So order of V for Q. What else is remaining? You have a dictionary in which you are storing distances. What happens to that? That will also take order of V. Similarly, you have a set called visited. That will also take order of V. So total is order of V only. So total space complexity is order of V. So for the breadth first search algorithm, space complexity is order of V. Time complexity differs on the representation of graph. If it is an adjacency list representation that is used, then your time complexity is order of V plus C. If it is an adjacency matrix representation that is used, then your time complexity is order of V square.